Hello and welcome to HCI 509, Research Methods and Statistical Analysis. In this lecture, Lecture 11, we'll talk about ANOVA. ANOVA, if you recall, stands for Analysis of Variance. It's a widely used statistical method to compare the means of two or more groups. When there's only two means to be compared, we simplify ANOVA to just be t-test. It's a lot easier to work with, but it's a rarefied version of ANOVA, if you will. ANOVA tests normally return a value called the F statistic, so we refer to ANOVA tests as F tests. First, let's talk about one-way ANOVA. So one-way ANOVA is good for studies that adopt a between-group design. Remember what a between-group design entails. And they only investigate one independent variable with three or more conditions. Let me ask you, what if we had one independent variable with two conditions? Would we use the ANOVA or could we use a t-test? T-test. Here's an example of one-way ANOVA. Suppose the goal is to investigate whether the use of a word prediction software has an impact on typing speed. Remember, that follows the same example that we used in the last lecture. But in this case, suppose researchers are also interested in speech-based data entry and would like to compare the three conditions: text entry using the standard word processing software, which will be our baseline, text entry using word prediction software, and text entry using speech-based dictation software. So you're going to find that we'll have three different means to evaluate. That's more than what the t-test can handle. Now, it may make sense initially to think I can just compare the baseline, which is the word processing software, to the word prediction software, and then I can make another comparison between the word processing software and the speech-based dictation software. But that's kind of a bunch of different t-tests, and there could be factors that are hard to explain. It's better to use a single test which can give us the result instead of worrying about doing all sorts of different mini statistics. So the independent variable of the study has three conditions, right? We have one independent variable, and that's the type of software. And then with the between group design, so it's three groups of participants. So if we have 8 people to take each of these, we'd need 24 total participants. And in JASP, the layout would look like this. Now, it looks very similar to the between group design that we had with the t-test, except for the fact that in the coding column, we have a 0, a 1, or a 2, which refers to the three different types of software. That's our independent variable. The dependent variable is the task completion time. So the only important columns in JASP are the third and fourth. So the returned F value we find is 2.174, and that's lower than the value at the 95% confidence interval. Okay, so if the F statistic is less than the statistic at the confidence interval, we cannot reject the null hypothesis. So it doesn't meet the threshold we want. So we conclude that there's no significant difference among these three conditions. So we would report the results as follows. A one-way ANOVA test using task completion time as the dependent variable. Notice we have to specify what we're measuring as our dependent variable. And group, I might change this to the software as the independent variable. Remember, we have three different conditions. Suggests there's no significant difference among the three conditions. We have F2, 21 equals 2.174, NS, which means not significant. So for factorial ANOVA, this is appropriate for studies that adopt a between group design and investigate two or more independent variables. So if you recall the study that I mentioned about hiring participants, and we looked at race, gender, and age, this is the type of ANOVA test that we did. So if we use the same evaluation study, let's just add something to it. Let's say in addition to the different software, we also want to know whether the different types of tasks, such as composition or transcription, what they have on performance as well. Not only are we looking at 3 different types of data entry, but we're also looking at 2 different types of tasks. So we have a total of 6 conditions. The data layout for running this test is more complicated than we saw in the one-way ANOVA test. So we have the task completion time in a single column in JASP, and a separate coding column is created for each independent variable involved in the study. So we have to have 2 separate coding columns. It looks like this. So the 5th column denotes the type of task. So remember, we had transcription, and then we had composition. Then we have entry method coding, which is 0, 1, or 2, depending on the type of entry method that we chose. And you can see here, we also have the task type. So we have 2 independent variables. We have coded in columns 5 and 6. And then we also have the task time in column 4, which is the dependent variable. Now let's talk about repeated measures ANOVA. So this is good for within group studies that just have 1 independent variable. Perhaps we're only interested in the impact of the text entry method. So we have 3 different types, right? We have our control, which is our standard. We have prediction and speech. But remember, this is a within groups design. So each participant is going to take and get a time for each of those 3 different methods. So the 2nd, 3rd, and 4th columns indicate the scores in terms of time, which is our dependent variable, for each of those different entry methods. So the 2-way repeated measures ANOVA is good for a within group design that investigates 2 or more independent variables. This goes back to investigating the impact of both the text entry method and the type of task. So we need to be very careful. Now, this is with the within group design. So we have transcription and composition, and we have 6 total columns, each with a separate time. And you can see here that we have standard, prediction, speech. Standard, prediction, speech. Those are repeated. The first 3 are for transcription. The second 3 are for composition. So it's important to arrange this in a way that makes sense. The column heads are going to give you some information about how to do this kind of analysis and what the results are going to look like. So let's say we got this kind of result. Notice we have task type, we have the error, we have the entry method, we have the error with the entry method, and then we have the task type, and there's times entry method. So this is looking at the interaction between the 2 types, because maybe there's some kind of correlation we have to address. And then we're looking at the error for that. So we get a sum of squares. You see the degrees of freedom. You get a mean square. We get an F statistic, and then we get a significance. And you can see here the task type is the only one that looks like it's got a low enough level of significance if we test at the alpha equals 0.05. Let's take a look here and try to understand how to report this. So the task type has a significant impact on the time spent to complete the task. F17 equals 14.217. So look at that. That's the very first line. We have 1 degree of freedom, and then we have 7 degrees of freedom for the error. There's no significant difference among the 3 text entry methods, and we have F2, 14 equals 2.923 ns for non-significant. Going back, you can see that's where we get the second line that has an F in it. So it's actually the third line down. But you see where the degrees of freedom, you have 2 and 14. This is reported to us. And you can see here we have an F statistic, and instead of reporting the significance, we just say NS. The interaction effect between the two independent variables is not significant either. 2, 14, 0.759 NS. So if we go back, we can see where we get that from the task type times entry method. So that's the interaction between the two effects. And you can see here, the F statistic is 0.759. Higher is better, of course. And you can see here the degrees of freedom are 2 and 14. So what do we do when we have a split plot design? Remember, that's where we have both between group and also within group components. So we want to study design that includes both. So one is going to do the transcription task using all three methods, and the other is going to use the composition task using all three methods. So you can see here, we've got the between and within because they're not doing all six. They're just doing one type of task, but they're using all three different methods or software tools. The type of task is a between group factor, and the entry method is a within group factor. So we have to specify, we have to have some kind of coding, which we do with the between group, to specify the value of the type of task. So here we have task type coding, where we have 0 or 1 to refer to the transcription or the composition. And then we have 3 separate columns for the scores what they got using each text entry method. So here's some of the assumptions we have to be aware of. And this is for both the t-test, which we talked about in lecture 10, as well as f-tests, which we're talking about here. So before we run the test, it's important to make sure that the data meets the assumptions of the two tests. So if we don't, we may come up with some incorrect inferences from these tests. So here are the 3 assumptions. Errors should be independent of each other. The errors in the data need to be identically distributed, and they also should be normally distributed. So remember we talked about random versus systematic error? Well, we want to make sure that we have these errors, if there are any, that are random as opposed to systematic. Because if they're systematic, they're not going to be independent. They're not going to be identically distributed because they tend to go lower or they tend to go higher. So if the errors are not independent, then we could have misleading information. So if one investigator gives more information than another in terms of instructions or answers some questions or gives some hints, then the participants that did it with the more detailed instruction might be consistently better. Now, if you remember, we talked about how this could happen with systematic error, and this is one example where it could occur. So the errors of the participants who were instructed by the same investigator are no longer independent, and we would not be able to say the test results are accurate. We also want to make sure we have what's called homogeneity of variance. So when we have multiple groups, we want to make sure that the variances are kind of equal. Imagine we got a bunch of heights of people. When we compare the means, if the variances of those two different groups have a nearly equal bell shape curve, then we will be in good shape. But if one is very wide and one is very narrow, that could mean that they're not identically distributed. So we have to be careful because transformation techniques such as square roots, logs, and reciprocals, we can use those to make transformations to get them so the variances are nearly equal. So we also have to make sure that they're normally distributed. This is very similar to the homogeneity of variance, which is the second assumption we just looked at. We only consider it to be violated when there's a high kurtosis or skew to the data. So when they're not normally distributed, non-parametric tests should be used, or we can also do things to bring them back to a normal distribution shape. You can see below, what we want is the purple one on the left, but if there's a right or a left skewed distribution, and look at how the mean and median differ, and that's one way these descriptive statistics can help us learn this. And if one is very different than the other, the mean is very different than the median, this tells us that we could have a non-normally distributed data set, and we can't use the F statistic or the T statistic. Thank you, and I hope this has been informative. I look forward to seeing you next time.